I would like to thank the invitation or the opportunity to give this talk. So as you will see, I will show a setup which can be used to tune the layer distance in van der Waals heterostructures. And I just start due to sake of time. I think there have been beautiful, works already shown in this workshop about Moire. So this is one of the figures from one of the latest reviews on this Moire physics, and what you already see or feel from these previous talks that just by these twistronic structures you can create flat bands, and you can have a wealth of interesting correlated states or ground states in these systems. What people have just dreamed of or worked for decades in correlated physics. And what is interesting for us also that these energy scales which are involved are in the millielectron or 10 millielectron volt energy ranges, and the origin of this correlated state stems from layer interaction between two layers. So obviously, if you can modify the layer distance in such systems, that would be a really interesting tool to address these correlated states, to tune their strengths and so on. And I will not go that far today, but in order to tune the correlated states, what we can do first is we just try to understand the single particle behavior of this system. Here is an artistic view. What you can imagine, you can have a twistronic system with twisted, let's say, bilayer graphene or twisted double bilayer graphene, and you can try to press these layers together, maybe with an advanced gate control. So here is what we imagine what happens in such a system under hydrostatic pressure. So you have a van der Waals heterostructures where you deposited layers on top of each other by standard stacking methods. And we believe that when you apply hydrostatic pressure, what you mostly change is the layer distance in these structures. So with that one, there are several interesting things you can look. For example, there are already 2D materials like Waals semimetals like tungsten telluride or something like this, where the band structure is really sensitive to the layer distance. So there you can already, by tuning just this structure, you can achieve interesting things. Or the other, which I will reflect on, is change proximity couplings in such systems or superlattice effects. And I would like to also say that there are people in the field working on this. So there are beautiful works from the group of Matthew Jankowitz. But to be honest, if you go, if you look far away, you know that this hydrostatic pressure cell is something which people have used in solid state physics. It's in some sense a conventional tool, but for Moire or van der Waals heterostructures, this is just not used, except these studies from this group, as I said. So the problem is probably because you want to integrate a system, where usually you usually put crystals in such systems, and then when we do nanofabrication, we usually use chips and bond them and so on. And somehow you have to make this work together, which is not impossible, but it's challenging. And we have developed a kind of a unique system where you can do this. So this is like our setup where you can place your nano circuit on a circuit board, and you can just bond them like every chip you would do. And then you can place this in a hydrostatic pressure cell. In these cells which we use, you can apply, let's say, 2-3 gigapascals of pressure. And since there's a pressure mediating medium, which is kerosene, you have to protect your samples. But we have shown that HBM can do this, for example, for you. And one thing I would highlight, that this requires nothing special sample preparation. So all of the samples which I will show are done for, in some sense, separate purposes than our pressure cell. But you can just take them, you can rebond them, and you can put into our pressure cell. So you don't need special tools to be able to silver paint them and so on. You can really use small samples as usually you do. And this is one of our first studies on this system. What we have studied here is a tungsten selenide graphene heterostructure. So we have previously shown together with a group of Christian Schoenberger in Basel that if you place a graphene on tungsten selenide, then you can induce in graphene a proximity spin orbit coupling. And we studied this proximity spin orbit coupling with localization measurement. And now what we have done is that, on a sample where originally did not show really signs of proximity spin orbit coupling, we applied hydrostatic pressure. And what we have seen is that though the transport properties did not change much, maybe the diffusion constant changed like 20% or something, but you see a clear transition as a function of pressure from a weak localization to a weak anti-localization, which we attributed to, to hydrostatic pressure, to the changing of layer distance and boosting of the spin orbit coupling. This shows that I think this system is ideal to change the layer distance, and obviously, for proximity structures, this is something which you can use to to boost or to understand the physics behind this system. Now I will move to Moiré structures. This is my take on lattice on lattice. Probably you have seen such figures already. So now what we will look is twisted bilayer graphene on bilayer graphene on bilayer graphene. I have worked a bit on Moiré heterostructures when I was in the group of Christian Schönenberger, where we have studied, graphene HBN superlattices. For example, I think we were quite happy that we could measure supercurrent with superconducting electrodes on a graphene HBN superlattice, or to see Fabry-Perot oscillations in locally defined cavities. Or I think we were, let's say, the first one to observe, double Moiré or super Moiré structure in graphene HBN structures. Compared to graphene HBN, what is different in these magic angle things that most layers are conductive. So there's a strong hybridization between the system. And for example, here what you can see is this is what usually people show. From the twist angle, you rotate also the Brownian zone, and at some point, the bilayer cones start to overlap. And if there's interaction between the bands, you start to open up a band gap. And now if you look a bit more precisely for the structures which we will use or which we measure, this is calculated for a twist angle of 1.06 degrees. This is not the magic angle, not so far from it, but it's not the magic angle for twisted bilayer graphene. What you see is that you arrive at such a band structure. So these are the single particle gaps, what you get from just the periodic potential. And what is nice in bilayer graphene, that with the displacement field or electric fields, you can also control via the layer polarization also the band structure. So what you can see is that you can open up a band gap, for example, in this structure at the charge negative point with an electric field. So these calculations were done by us following the paper listed here, where many of the parameters which we needed have been already calculated. So what happens with pressure? This is shown in this figure, what we expect. So there's this band structure of twisted double bilayer graphene with the band gaps shown here. And what you see is that when you start to apply pressure, let's say this is calculated for 2 gigapascal, what you see is that these bands start to shift down, the conduction band shift down, the valence band shift up a bit, but all these single particle gaps are closed in the spectrum. So this is something which should be quite visible in our experiment. Maybe one thing I didn't address here, so I go back. So with the electric field, what happens here in this one, that you split up this central band structure, and what you see is that these bands go up and down, and finally the Moiré band gaps are also changing. So now you have two knobs on this structure. One is the pressure, which is less tunable than the electric field, so you have to warm up your sample in order to change the pressure. But still, you can you change the layer distance, and there's the electric field, and with these two, you can engineer your band structure, not at will, but you can substantially change it as you see. So the structure which we have looked at is a twisted double bilayer graphene. This was fabricated at ETH Zurich. What you see is that this is a top and bottom gated device in a whole bar kind of structure. And this was from Brown's-Zach oscillations for magnetoconductance measurements. You can get that this was really around at 1.06 degrees, as I said before. And I would already note before, maybe this question could come up, that when you apply a pressure, we didn't notice any change of this alignment angle. You change a lot of things, but this alignment angle doesn't change, it seems, in these structures. So here is the measurement shown as a function of displacement field and carrier density. So using a top gate and bottom gate, you can do this. And let me guide you through this picture. So what you see is the resistance. So what is bright color? It's high resistive state. So this is the orange dashed line is the zero displacement field. So you see that here, if you go through, you reach two large resistance states. And if we look again the spectrum, what you see here is that what you do is that you move your Fermi energy, and this band corresponds, this bright region corresponds to when your Fermi level lies in the band gap, Moiré band gap in the conduction band, and when you are in the valence band, this corresponds to this structure. You might also see that, you know, maybe it's not so visible, but this band gap or the resistance starts to decrease as you increase the electric field. This comes from the fact that, you know, you really starts to close this gap. This is shown also with this green cut with the finite displacement field. What you see on this green cut that there's already, you know, a splitting of the central band of the Moiré band, and the Moiré gap starts, the single particle gap starts to shrink here. And these correspond to, you know, so when you are, for example, in the charge net point and you look at this gap, this corresponds to these bright features. So this is the central part when you are, you know, at the Dirac point and you start to open a gap with the electric field. So how to get these gaps? So what we have done is that we did thermal activation measurements, you know, to get these gap size. We use such maps and fitting procedures as done in the literature, also by others. And here is a summary of what we have found. So these are, you know, the gaps as a function of displacement field for 3 positions, still without pressure. So this is the band gap at the positive electron side. This is the red one at the hole side. And what you can see is that with the displacement field, you start to close these gaps. This is also shown here. And the other one, the black one and the charge point, you start to open them with the displacement field. Okay, this is what you expected from the calculation, and also it matches what other people have shown. And now I show in this slide what happens with pressure. I try to guide you through. So this is the 2 colors now corresponds to the 2 different pressures. The red one is the one which we have looked before. This is with 0 pressure. And what you see is that when you apply pressure, these are the blue points, you completely close the Moiré gap. In the charge 90 point, there's a bit of change in the slope, but there's not much difference compared to you know, absence of pressure at 0 pressure. Whereas if you go to the whole side, again, you almost completely close the band gaps. You really have small gaps, you know, on the millivolt energy scale. Here, I must admit, you know, that when you go to such low energy scales, you are not really certain how precise you are in extracting these band gaps. I think, you know, this is usually the case. So this is our calculations, how these band gaps should evolve as a function of displacement field. Here it's scaled with the on-site energies of the layers, but the tendencies you can clearly follow. At 0 pressure, you know, the electron side single particle band gaps, sorry, it's rotated now, but this is the electron side. It should close with the displacement field as seen in the experiment. On the whole side, it should also close as seen in the experiment. It doesn't close the same way exactly as calculated in the theory. I can come back to this if you want. We have some ideas why it might deviate, but, you know, the tendencies are the same. How the single particle band gaps are opening up, it's also similar. And with pressure, you also see that, you know, at 0 displacement field, the band gaps, the Moiré band gaps are closed. I think on the whole side, it's clear that you don't open this band gap up with the displacement field, which matches kind of what we see. Here you expect to rather open up quickly this band gap on the electron side, which we don't see. At higher electric fields, we start to open it. So this is something which, you know, quantitatively doesn't match our experiment. Before I give the credit to the other people, I would like, because there was already some discussion on what kind of tuning parameters you can have in these heterostructures. I would switch gears and in 2 slides show another kind of tuning mechanism. So what is strain? So now I have shown pressure, which can, you know, be used to change layer couplings. Strain is something which I believe can, you know, change the symmetry of the systems, or you know, if you do nicely, maybe you can do pseudo-magnetic fields as shown before or something like this. So what we have developed when I was a postdoc in the University of Basel is a setup which you can use to, strain, in this case, graphene heterostructures. Well, what is nice in these structures is that you can perform transport calculations transport measurements and straining at the same time, on high mobility devices. So I think there are a lot of measurements, where you can optically measure systems under strain 2D materials. But it's rare that you can have, like 100, 200,000 mobility graphene samples and apply strain at the same time. And we have achieved this by, straining fully encapsulated devices via edge contacts. There's a limit how much you can strain, but I guess you can think that up to 1% you can surely strain these structures. And so this is a sample holder which we have developed. You can measure at low temperatures, in this case, it was 4 Kelvin setup. We have verified via Raman that, we can really strain graphene. And for example, one thing which might, I think can be relevant also for graphene superlattices is that we have found that with straining, we can, for example, increase the mobility of graphene heterostructures. Quite substantially in this case, a factor of 2 almost. And via some studies, we have attributed this to reducing strain fluctuation, out of plane strain fluctuations in graphene, so to flattening out graphene. With this, I think my time is more or less up. So I would like to thank for all the people who worked on this. So Szabolcs was the one guiding the development of these pressure cell studies. Balint and Albin were mostly in this setup. So they are PhD students in Budapest in our laboratory. Balint was the one who worked on the twisted bilayer graphene, also on the experiment and the calculation together with Andor Kormányos from Eötvös University. We got the samples from ETH Zurich, from the group of Klaus Hensel and Thomasin, and I really owe a big debt for Peter Rickhaus trusting us their samples on, and it seems that it works. And these are the people from the University of Basel who I worked with on the superlattice structures or in the induced proximity effect. And with this, I would like to thank you for your attention. And in some sense, this is the time for a divestment. So, we are happy that we have this setup, and we are happy to share with people who have interesting samples to measure. Thank you.
Thank you very much for this great talk. I see already a question from Lino Pereira. You want to ask your question?
I'm sorry, that was for the previous talk, but then
we
were
I
over
see.
it. No worries, no worries.
All right. Any other question? Or all right. So this you showed like some great capabilities. Maybe you've mentioned it. What type of field and temperatures?
So I think at the moment what we have is a VTI system, to go up to, I don't know, 9 Tesla or 3 Tesla vector field, and from 1.5 to 300 Kelvin. But I think there's nothing preventing us to putting it to, we already have more or less the converters to put it into a dilution free. So if you, from my perspective, probably the most interesting is going into this twisted correlated phases, where some of them is really needs lower temperatures than maybe a VTI, but I think that's not really an issue for us. So
great. I have a question from Jana.
Yeah, so thank you very much for a very interesting talk. So maybe I'll have more practical question regarding your setup. So what is the spatial resolution for your Raman, and how you really control the temperature on the sample if you are
so for the
helium?
So this relates to the straining setup. So that's a conventional Raman setup which we have used Okay, so there are two things. So one is that we measured Raman at room temperature. I go back to the figure, at room temperature. So, it's a conventional, I think, you can say safely 500 nanometer spot size. So this is, your resolution. In this paper, we have, maps around the sample, like let's say these 10 micron flakes. You can check how homogeneous uniaxial strain you can generate, or in this case, we generate a bit of biaxial strain. The measurements were done at a low temperature setup where we didn't have at that time capabilities to do Raman. So, by combining room temperature measurement and mechanics, we have some estimates also from other things, how much strain we have, but this we didn't have. Now I think there's development done at Basel to be able to do this at the same time. It's a bit more challenging, but I think it will work. So, but I think, it will be 500 nanometers or something like this.
Sorry, I missed that the measurement is done room temperature.
So sorry?
So I just missed that the setup for the measurement.
No. So I think I didn't emphasize this. So this is at the moment 2 separate setups, but I think it's maybe already operating more or less at the same time. But, I think it's really like conventional 500 nanometer Raman setup, 500 nanometer spot size.
Okay, thank you very much.
You're welcome.
Maybe one last question from Yuval Ronen, quickly.
Thanks for a great talk. I wanted to ask, probably I missed it, what should be the effect of the strain on the twisted, like that should reduce the disorder that Eli was talking about, or what do you imagine happening?
That's a great question. I'm in some sense, I was wondering recent times in the same, but I think my idea is, okay, that there are different claims. I just read these claims in some sense about what limits, for example, sample quality in these heterostructures. And we heard one today, for example, that it's angle, like a rotation angle fluctuation, or how to say twist angle fluctuation. Some other, in other papers, they state that, it's heterostrain. So when one layer is strained with respect to the other, which I think can also give signatures of what we have seen in the squid measurements, because there you really change the angle. So I think, if you can strain one layer a bit more than the other, then I expect a large change, because, you really change the moire unit cell with, in this structure. One can also imagine that, like in this case, what I show in this figure, that you can, flatten out some of these fluctuations, you strain, and then it become, the two lattices, I don't know, the two lattices convene to each other much better, and you see a more homogeneous. I think it's completely unknown, but my feeling is that it would be interesting to test. So
no, definitely. Thanks.
You're welcome.
All right, let's thank the speaker again.